All right, wave nature or particle nature of light continued. So we're looking at diffraction and partial transmission and partial reflection. So it's going to be some review of grade 11 topics and connection to this, gathering of evidence one way or the other. And so diffraction from grade 11, probably remember that, it's a change in direction just because of going past a barrier. So you can think of these wave fronts of a bunch of Huygens wavelets added up, and then basically a single Huygens wavelet, would spread out. And so if you're restricting it down, that's kind of the idea. But you get the curvature back of the reduced number of wavelets. So we're thinking of viewing this from above. If light can be observed to diffract as well, then pretty good evidence of light exhibiting wave properties, right? So that's kind of the idea. So this is what we know in the past about diffraction, right? Going around the barrier, you get some of the bending back, and so you can think about a Huygens wavelet here. The curvature showing up because it's not combining with a bunch of other ones anymore. Same as if you reduce this down, one Huygens wavelet fits through, and you're going to see the circular waves, right? So I'm already looking at the wave description. Here's some other properties that we know from grade 11 that were covered in grade 11 anyways. If the wavelength is big, the amount of diffraction increases, right? So if you have larger wavelength here, you're going to get more and more diffraction on the other side. Generally, the wavelength needs to be large relative to the size of the opening, basically. That's what this was about. But just in general, even if it's not an opening, it's still gonna have an effect, right? So notice the words here. If you're not as familiar with these, you want to try not to get them confused, right? Refraction would be a change in direction due to the speed of light changing as it goes into a new material, whereas diffraction is a change in direction due to just traveling past a barrier through an opening. Okay, they sound kind of similar, can be confused with one another. So I just want to clarify that. So evidence of this, right? So diffraction. Well, Newton said light doesn't diffract. That was his, and there's certainly no way to explain it in terms of particles as far as Newton was concerned. Now I've got quotes and an asterisk on there. You're going to see in a future lesson that quantum mechanics gives actually a pretty good explanation of this, as it turns out. So eventually, once we piece it all together, that'll mean more to you. What the heck is quantum mechanics, right? So here's the deal, though. Light does diffract, right? It's just not super easily seen in nature. It's harder to demonstrate. It wasn't known at the time, right? So the wavelength of light is really small, right? And so think back to this, right? This is why I'm reviewing this, right? If the wavelength is super small, it's going to be hard to notice diffraction, and that's exactly what is true about light. The Huygens wavelets discussion we talked about, though, is very obvious. You can demonstrate it with water waves easily. This is actually a picture from nature where these breakwaters that are designed to help stop erosion of the shoreline, and then so those plane waves come in, straight waves come in, and then diffraction happens, and the wave that gets to the shore has got this curvature, and it erodes away the shore less because of it. You get this deposit of material that would have been gone otherwise, and so on. Kind of a neat thing, but very clearly diffraction in nature and so on, right? Gravity could have been, really, I'm surprised Newton didn't sort of think of it, but gravity could have been an explanation for diffraction. Just like the light passing by the sun is affected by gravity and so on, but gravity is not strong enough to cause diffraction. If gravity had a strong enough effect on light, diffraction would easily be explained by being pulled to the side. Trouble is, of course, there's not a lot of mass there and just not enough gravity forces, right? So this is not the cause of diffraction, but kind of surprised Newton didn't think it was. So diffraction, you want to see it yourself? If you have a finger and thumb handy, you can do it. All right, so look at your finger and thumb, look between your finger and thumb towards the light source, like in this picture, okay? And slowly bring your finger and thumb closer and closer and closer together, and observe what happens just before your finger and thumb are actually touching. Okay, so pause the video, look at it, try it first, do it now, right? All right, so what you'll see is, describe it as a little wart that grows between your finger and your thumb. You're not actually touching it, but darkness appears there, right? You zoom in on it, You're not actually touching it, but it's like there's an area there where it's dark. Okay, well, what's happening there is light that should be coming towards your eye through that gap diffracts, bends away from your eye. So now light isn't coming towards your eye from that spot, and so it looks dark there. Okay, so that is that's a diffraction, easy way to see it. This is a little video doing that. So this is what you should be seeing.
Touch there.
Okay,
they just get so close.
Turn up the diffraction volume. You're my old self here.
My fingers don't actually touch there. They just get so close that diffraction diffracts the light away.
Pause the wrong thing. I tried to pause the video and I paused the lesson. So let me go back to it.
Diffraction diffracts.
So diffraction diffracts the light. A diffraction bends the light, so it doesn't end up going to your eye. Right?
Light away from your eyes, so you see a dark lump.
Okay. So that is that. Next thing here. So observation to do with this, of course, as we said. Come on, delete. The space between your finger and thumb gets dark before contact is actually made. The explanation is light that would normally be going through and getting to your eye diffracts away, changes direction, no longer reaches your eye. Okay. Do you notice anything else? Go and look at it again. Look super carefully at it. Notice anything else? Be a critical thinker, right? So let's do this. Okay. So I wanted to actually change my lesson to be like this. So here's the close-up image here. Do you see anything there, right? So if you look carefully at it, you should see a little pattern of light and dark bands. And so that's this right here. You can see like just ghost image there of lines, streaks. It looks like someone took an eraser and just sort of smudged it horizontally, right? Those are actually interference bands, which we'll understand later on we'll review over later on. We've already done it in grade 11, but yeah. So that is bands of interference patterns. So light showing interference even. Check that page out and the link out if you're interested at it right now. But down here, when we get to that lesson later on, I'll be referring back to this, of course, right? But it's constructive and destructive interference of light, which you've already seen in grade 11 in the sound and waves unit with water waves and sound waves even. Okay, so very clearly a wave property. So yeah, light diffracts. Here's diffraction again. There's a pole there. The sun's behind, and the sunlight's bleeding around that pole. While sunlight that went on the side of the pole diffracts and it changes direction, ends up looking like it came from somewhere that it didn't. Right. So this is there's another version where there's this opaque disc, lights shined at it, and then they get this bright spot in the middle. It's called Poisson's bright spot or Poisson's disc. So a little dot in the middle is because of diffraction. In shadows from like a screen, especially if you have like a point source of light, you'll see in the middle of the shadow, you'll see a little bright section. So this is a photo I took. See a little faint bright section in the middle there, right? So this is in the floor of my boat, and so there's a spot on like the wakeboard tower that was like shiny and really bright point source of light, and it was casting this image. It was like near sunset time, and so like it was projected on the floor from the spot. This one I believe was in my old house, and there was a spot from a mirror on a car, like the curved back shiny part of a mirror, and it was a bright light source, and so this is a shadow on the wall and in the room that had a screen on the window. So diffraction. Yeah, particles, not so much of an explanation, not without quantum mechanics, as it turns out. So a bit of a twist coming later on that. But for now, we'd be like, yeah, wave property all day long right there, right? Until you learn more. Okay. Dispersion. So dispersion is obviously white light, all the colors splitting up into all of the individual colors, right? So all the colors together is white, splitting up into all the individual colors. You can see the rainbow. So Newton claimed, basically Newton said, oh, that's because masses of particles of different colors of light are different. And so, more mass means more inertia. And so in this case, you'd think like, okay, the red has more inertia, so it didn't bend as much, is the idea that he put forward as to do with it. So all that stuff, right? And then with waves and with waves, refraction is observed to depend on different frequencies, which you saw in a previous lesson. Frequencies and wavelength is different colors, right? So it's not because of mass. It turns out that particles of light are, of course, massless, right? And so, dispersion and why, like the question that I'd like you to be asking and thinking about is like, okay, well, why does wavelength affect the amount of diffraction or dispersion, I should say. Dispersion. So it goes along with even like why light even slows down in the first place, right? So then extend to that, why different colors of light slow down by different amounts. These are all good questions that good critical thinkers are going to ask about. A way to remember it for me, but it's not really necessarily what's going on. But again, scientific models, right? If you have a model, it helps you remember things and so on. It's helpful, right? But if you look at purple blue end of the spectrum is the high energy stuff. Now I always thought of it as like the high energy stuff is going to interact more with the particles, and so it's there longer because it's interacting with them more. Or you could look at it as it's more energy transferring to the particles because they're so energetic. It's just a way of trying to remember it, right? Whereas the red can slip through. I even in class I described like you're trying to get through a crowd, and what's easier way to get through a crowd? Just sort of keep your arms at your side and sneak through, like fitting through the cracks in a crowd of people. Or if you put your hands out and you're lunging your arms out back and forth trying to go through a crowd, you're going to interact with people, and that's probably going to slow you down because someone's probably going to get mad at you, right? So it's just a silly way of thinking about it. So my official model of light isn't a little person with arms jutting out and punching people, but again, a little weird scientific model helped me remember it, right? That the blue end of the spectrum, purple end of the spectrum, refracts more and causes dispersion. So textbooks describe, how wavelength affects the amount of refraction. It's seen with waves and so on. Points out that you can think of like this being a good model for light as well. I think it's the reverse, right? It's the reverse of what we encounter with water waves. So mechanical waves and waves of light might not have the exact same kind of properties. So wave theory supports the idea of dispersion in general, and people argue that light is made up of all the colors of the spectrum, and they all bend by a different amount, and so on. Now they do say here, we'll see later that the explanation is more complex, but basically, it's pretty satisfactory explanation that wave properties support the idea of dispersion. Now, that more complex thing is summarized in a pretty awesome video here by 3 Blue 1 Brown. I don't know if you've ever seen this site, but they're really, really good. So I'm gonna play this. I think I'll just play it because I want to be able to commentate a little bit as we go, and I'm hoping I don't get dinged with copyright stuff. I'm pretty sure it's considered fair use. It's an educational video. This is an educational video, and of course I'm saying their name and giving credit and directing your attention towards their site. So I don't think they'll mind. So I'm gonna play it. It is going to be on like a little bit fast forward. It's going to be on like 1.5, I think. So hopefully you can tolerate that, but just make it not take as long here. So it's on 1.5. Here we go. Sound up.
I realized recently that I didn't really understand how a prism works. The standard explanation, what you might hear in a high school physics class, for example, goes something like this. When light enters a medium, like glass, it slows down, in the sense that if you look at the crests of the wave, in a vacuum, those crests are traveling at c, the speed of light, but inside the glass, those crests will be traveling a little bit slower. And the specific ratio between the speed of light in a vacuum and the speed inside a medium like this is called the index of refraction for that medium. The reason we use the word refraction instead of, say, the index of slowing is that if a beam of light enters this glass at an angle, then a consequence of this slowdown is that it bends a little bit, or using the lingo, it refracts. And the way my high school physics teacher always explained this was to imagine a tank going from some region where it can travel relatively quickly, like concrete, into something slower, like mud, where if it's coming in at an angle, then as one of its treads hits the slow region first, that tread will be going slower while the other one is faster, causing the whole tank to steer a little bit until that second tread also enters the mud, then it continues straight, just traveling a little slower.
Now, of course, this isn't the tank theory of photons or of light. It's just a model. This is just more of an analogy, if you will, that helps you remember something. Sometimes scientific models are like, hey, for a while we thought that electrons really are orbiting, and so on. Right? No one thought that light was like little tanks. But yeah, here we go.
We'll get back to the actual reason for bending in a bit, but at this point, the high school physics students typically learn a law known as Snell's law, which specifies exactly how much things bend. If you draw a line perpendicular to the boundary between the glass and water, and consider the angle between that perpendicular line and the beam of light, then Snell's law tells us that the sine of this angle divided by the speed of the light is always a constant. So the slower the light, the lower that angle will be, and that lets you actually calculate how much things refract.
So it's called Snell's law because it's just an experimental result. You see that it always happens, right? So it's just, this is what happens. Now, it doesn't explain anything to do with why it's happening, right? So here we go.
What's going on with a prism, then, is that the specific amount that light slows down depends a little bit on its frequency. For example, blue light, which has a relatively high frequency, would get slowed down more aggressively than red light, which has a relatively low frequency. Now, most of the light that you see is not a clean, pure sine wave. In particular, the white light coming from the sun is not a clean sine wave. It's something much messier, but it can be expressed as a sum of a bunch of clean sine waves.
Which I really like because in grade 11 we've done this, right? The idea of superposition of waves. So if you superimpose all of the different colors, all the different pure sine waves of different frequencies, you get this complicated wave that we see as white light. Pretty cool.
And corresponding to a pure spectral color. So when you shine white light into a prism like this, all those different components get refracted by slightly different amounts, causing this iconic separation of the pure rainbow colors. So that is the standard explanation, and it's not wrong per se, it's just that all of the key components are handed down from on high. Like, why would light slow down like this? And what exactly do we mean by slowing down? And even if you understand that, why would the amount that it slows down have anything to do with the color of the light? Is that just a coincidence, or is it necessary? If you have a sufficiently high standard for explanations, you want both of these facts to feel discovered, rather than...
I like that idea of, like, if you have a sufficiently high standard for explanation, you're asking why. You're not just accepting things because someone told you it, which is critical thinking. We want that, right? We want our scientists, we want our future physicists to have that. So yeah, I like this video to encourage that. So, these are observed to be true, and there's theories, ideas to do with it. But I mean, let's look at why it actually slows down and why it depends on frequency. Okay?
Feeling like they were handed down. The first explanation I saw that started to give this feeling came from the Feynman lectures on the matter. And a lot of what I'd like to do with this video is simply animate a lot of the key points that he makes there. It involves really digging in to think about each individual wiggling charge in the material and the propagating light waves caused by each one of those charges and how all of them superimpose on top of each other, which feels like it should be a complete mess, but it actually works out to be not only understandable, but satisfyingly explanatory. For example, it explains why it has to depend on color, and the key intuition there really comes down to what happens if you're bad at pushing a child on a swing. Bear with me, I promise that'll make sense later. Also, when I mentioned on Patreon the intention to cover this topic, a lot of people had a lot of questions about the index of refraction. For example, numerous people asked about how it's possible for this number to be lower than 1, which really does happen, despite that seeming to imply the impossibility of something traveling faster than the speed of light. There was also a question about birefringence, which is where a material can have 2 different indices of refraction, causing you to see double when you look through it. And that actually ties in really nicely to putting in the final puzzle piece from the last 2 videos about the barber pole phenomenon. And a couple people also asked about why light slowing down would imply a bending like this. And I agree that deserves a better explanation than the tank analogy. I promise we will get to all of these questions later, but it makes sense to first lay down some groundwork by spending the bulk of our time on the key question of why passing through a medium would change the speed of a light wave at all. And for this, I want you to think of your material, like glass, as being broken up into a bunch of distinct layers, all perpendicular to the direction the light is traveling. And we'll start by focusing our attention on the effect of just one of those layers on the light wave. The true effect would be minuscule, but if you'll let me exaggerate it for a moment, what it does is kick back the phase of the wave. And maybe it's worth a brief aside to make sure we're all on the same page when it comes to wave terminology. If you go and graph the function sine of x, when you put some term in front of it, affecting how high that wave oscillates up and down, that's what we call the amplitude. When you put a term in front of x, this will affect how rapidly it oscillates. If this is meant to describe a wave over time, that term would be called the angular frequency, whereas if it's meant to describe a wave over space, that constant would be called the wave number. Then if you were to add some other constant inside that sine function, and notice how as you change what that constant is, it sort of slides the wave left and right, that term describes the phase of the wave. So when I say that our light wave hitting a layer of glass causes its phase to get kicked back, I mean if you take whatever function describes it before it hits the glass, then the function describing it after that looks almost the same, just with a little extra something added to the input of that sine function.
Now this is just from one layer of the material. He's going to go through an analysis that'll show like the combined effect of the little phase kickback of a whole bunch of layers results in it traveling slower. Okay. anyways, nice review of some grade 11 math there too, right? The transformations, function stuff. So.
Like I said, in reality, that'll be a very small number, something proportional to the infinitesimal thickness of that layer, but I'll keep drawing it as something exaggerated and keep track of the value of that phase kick over here on the left. Let's say you go and add a bunch of other layers of the glass, each one also applying their own kickback to the phase of the wave. The question for you is, what does that new wave look like? If the value of that phase kick applied by each layer is something really close to zero, then the wave is hardly affected at all. But the larger that phase kick, the more the wave kind of gets squished together among all those layers. Admittedly, right here it looks all kaleidoscopic and weird, but that's really just because I have a discrete set of layers, each applying an unrealistically large kick. Notice what happens if I smooth it out by doubling the density of layers, but having each one only apply half the phase kick. And then I do that again, I double the density of the layers, but have each one only apply half the phase kick. As I continue this over and over, approaching a situation where you have a continuum of glass, each layer applying just a tiny infinitesimal phase kick, what you end up with is identical to, indistinguishable from, a wave that's simply traveling slower, oscillating up and down with the same frequency, but with a wavelength that's been kind of scrunched up.
So this changes the question to be, okay, so why does it phase kick then, right? If you're buying right now that the phase kick leads to it slowing down, well then, okay, now we have this new question where it's like, okay, why the phase kick then? Which is totally explainable. You'll see it relates to the previous things we've done in this course of addition of vectors, which is pretty cool.
Here is the first key idea with the index of refraction. Instead of asking, why does light slow down in glass, what we really need to ask is, why does its interaction with a single layer of that glass cause a kickback to the phase of the wave? And then when we want to get quantitative and understand exactly how much the light slows down, which is critical for understanding why it depends on color, instead the real question is, how strong is that phase kick? From here, it's helpful to turn back to the fundamentals of what light even is. This is something we talked a lot about in the last video, but a little review never hurts, so let me go over the essentials. As many of you know, light is a wave in the electromagnetic field, but here we'll just be drawing the electric field. The electric field associates each point in 3D space with a little three-dimensional vector telling you what force would be applied to a hypothetical unit charge sitting at that point in space.
Remember electric field intensity, force per charge, right? Lots of cool review from this course here.
The key thing going on with light is that if you have a charged particle and something causes it to wiggle up and down, that results in these propagating ripples in the electric field away from the charge. And that propagation is traveling at the speed c, the speed of light. Whenever those ripples happen to reach another charged particle, they cause it to wiggle up and down, albeit a little more weakly than the initial wiggle. And that in turn causes its own propagations. The way we describe this in the lab...
So that's going to be critical, okay? You have a vibration here, sends out a ripple. That makes this one vibrate, which actually sends out another ripple. And that's what's causing that phase kick. So that's something to lead ahead to.
Last video was that if at some point in time a charge is accelerating, then after a little delay, which depends on the speed c, the existence of that acceleration induces a force on another charge. We went over the specific force law describing this. It's something that can be derived downstream of Maxwell's equations. But for our purposes here, the main thing to tuck away in your mind is that the amount of time it takes that initial acceleration to cause any kind of influence elsewhere travels at exactly the speed c. And really, you should think of c not so much as the speed of light per se, but as the speed of causality. It determines how fast any kind of influence travels. It's just that one of multiple consequences of that is that it's the speed of light. In particular, when you get a charge oscillating up and down in a nice clean sinusoidal motion.
So to extend this, gravity, for example, like if the sun were to disappear all of a sudden magically, we wouldn't know for like 8.5 minutes because that's how long light takes to get here, and also its gravitational effect would take to get here. So we would continue in our state of orbit around the sun until the sun's not there anymore. Then the Earth would just continue in a straight line motion, right?
You can think of these rippling effects in the electric field as describing the force that would be applied to another charge sitting there as a result of that past acceleration. I will freely admit that I had a bit too much fun in that video just simulating how the electric field responds to accelerating charges, and that I'm kind of doing the same thing here. But there are two important facts for our pursuit of the index of refraction. The first is that when you have multiple different charges oscillating up and down, the net effect on the electric field is just the sum of what it would be for each individual charge, which is kind of...
That is a lot like Huygens wavelets, right?
Of what you would expect. And then the way that it shakes out is that if you have a row of charges oscillating in sync with each other, or for our purposes today, a plane of charges, all wiggling up and down in sync within that plane.
So these would just be plane waves going out here, and then he relates that to the idea of just a beam of light.
Then the effects of each individual charge tend to cancel each other out in most directions, except perpendicular to that plane, they actually constructively interfere. This is how you can get a concentrated beam of light. That's the important thing. If you have a layer of charges wiggling up and down in sync with each other, then even far away from that layer, it produces this nice sinusoidal wave in the electric field that we're so fond of drawing to represent light. When I draw a light wave like this, it's really only depicting the electric field on a single one-dimensional line. A more full picture of light in 3 dimensions would look something more like this. That tends to be a little bit busier, so usually we just draw the sine wave. So, thinking back to the question of why interactions with a layer of material would cause a kickback to the phase of the wave, let's start thinking it through. When a light beam enters a material, like glass, then it causes all of the charges inside that material, electrons or maybe the occasional ion, to wiggle up and down in response to that light wave. You might think that adding together all the propagations from all those charges is a complete nightmare, but we can think about it one layer at a time. As the light wave causes this layer to wiggle up and down, that wiggling produces its own second-order light wave at the same frequency. And it propagates in both directions perpendicular to that layer. The overall electric field, then, looks like the initial incoming light wave added together with the second-order wave. By far the most distracting part of what's going on here is everything on the left, and this actually corresponds to the light being reflected back. And from experience, you all know that when you look at water or you look at glass, light not only goes through it, but some of it gets reflected back. And we could have a whole interesting discussion on quantifying exactly how much, but in the spirit of staying focused, we will completely ignore that for today and only focus on what's happening to the right of that
In
layer.
the rest of our lesson, we're going to actually talk about that partial reflection as well. But here we go.
You can probably predict what I'm going to say. It turns out that when you add that second-order oscillation, the overall effect is almost identical to the incoming light, but just shifted back in phase by a little bit. And then because many successive shifts to the phase like this are the same thing as light slowing down, this will ultimately explain the index of refraction. But of course, the sufficiently curious viewers will now be raising their hands and asking, why is that the effect when you add them together? And so here it might be worth a little sidebar on how to think about adding two waves together. If you draw some sine wave with some particular amplitude...
Again, encouraging scientific curiosity, right? So he says it causes a phase shift. The video's not done. Like, you should be asking, well, wait, why? How did that work?
some specific frequency, and some specific phase, and then you draw another sine wave, also with its own amplitude, frequency, and phase. In general, it's very hard to think about what the sum of those two waves should look like as you tweak those initial parameters. In the specific case where the frequencies are the same, which is true for our example, the result will also look like a sine wave with that same frequency. But even then, it's a little tricky to think about exactly how to describe that wave. It has some amplitude and some phase, and if I ask you to concretely compute both of those numbers based on the amplitudes and phases of the initial waves, it's not immediately clear how you would do that without maybe throwing a bunch of trig identities at the problem. But here's a really nice way to think about it. Imagine that first wave describes the y component of some rotating vector. The length of that vector corresponds with the amplitude of our wave, and then the initial rotation of that vector corresponds with the phase of our wave. And then similarly think of that second wave as describing the y component of another rotating vector, where again the amplitude corresponds with the length of that vector, and the phase of the wave tells us the initial angle of that vector. Now to think about the sum of the two waves, just think about adding those two vectors tip to tail. And because they both have the same frequency, as both of them rotate, their sum kind of rotates in lockstep with them. So if you want to think about the amplitude of a resulting wave, it comes down to the length of this vector sum, and similarly the phase corresponds to the angle of that vector sum. In some cases, this tells you things that you probably already knew, like if the two phases happen to be the same, then you get constructive interference and you have a bigger wave that results. And
That's a nice little connect back to grade 11, right? The constructive interference.
if the phases were 180 degrees out of sync, then you get deconstructive interference
And deconstructive interference.
with a relatively small resulting wave. What's a little bit less obvious, but what's crucial for our discussion here, is that if the phase of that second wave happens to be exactly 90 degrees behind the phase of the first, so kind of a quarter cycle out of sync, and if that second wave is also very small compared to the first, then if you look at the little vector sum on the lower left, you'll notice how this means that the resulting wave is almost identical to the initial wave, but just shifted back in its phase by a tiny bit. Moreover, the size of that phase shift depends on the specific amplitude of that second wave. So looking back at our previous animation, where we have some wiggling charges in a layer of glass causing these second-order propagations that need to be added together with the incoming light, the way it works out is that the phase of that second wave is exactly a quarter of a cycle behind the phase of the first. So when you add them together, you get this little phase shift.
So there you go, right? I suppose you could ask, well, why is the secondary 90 degrees out of phase, right, as well?
And then, critically, the size of that phase shift is bigger when that second-order wave is larger, and then smaller when that second-order wave is smaller. Again, the very curious viewers will be raising their hands and saying, why does it work out to be exactly a quarter of a cycle behind? There is a very nice reason, but it's just a little too much detail for us today. If you're curious, I highly encourage you to take a look at the Feynman lectures on the matter. For our purposes, step back for a second and think about what you need to explain the key question of prisms, which is why the index of refraction would depend on color at all. As you now know, that index depends on how much each layer of glass kicks back the phase of the wave, and that phase kick depends on the strength of the second-order wave resulting from charge oscillations in the layer of that glass.
So presumably that second-order wave, that resulting wave that goes out because of the fact that that layer reacted to the original, disturbance. Presumably that's going to depend on the color, right?
So you need to drill in and understand exactly how much those charges wiggle in response to an incoming light wave. So let's zoom in on that layer and think of each one of those charged particles, and even though the specific molecular structure can be something very complicated, we're going to model each one of those charges as if it was bound to some equilibrium position by a spring, or maybe a set of springs. I don't mean this literally, of course. I just mean if we describe the displacement of this charge from its equilibrium with a little vector x that's going to depend on time, then in our model, the force applied to the charge...
This game, you're not ready for it.
Pulling it back to that equilibrium is going to be something proportional to the size of that displacement, with a little proportionality constant k. This is the same law that governs how springs work. You might ask if that's accurate, and the idea is that for very small displacements, it's actually a really good approximation. This is a very common thing to do throughout physics. We would call it a linear restoring force. The idea is that maybe the actual force law depends on the position in a much more complicated way, but we're basically taking a low-order approximation near the equilibrium. If I just run this as a simulation, plugging in this force law, here's what that displacement looks like as a function of time. What you get looks like a sine wave. This is called simple harmonic motion. And the frequency of this wave is going to matter a lot for you and me. And finding that comes down to solving a certain differential equation. Because the force is really the same thing as mass times acceleration. And the acceleration is the same thing as the second derivative of that displacement. So what we're saying is we want some function whose second derivative looks like a certain constant times that function itself. Any differential equation students among you might enjoy thinking about how you solve this. I won't go over the full details, but the answer is reasonably intuitive, and anyone who knows a little calculus can just check it for themselves. The way it shakes out is that if the initial condition is that our little charge has a velocity of 0, but it's offset from the equilibrium by a little vector x naught, then the way it evolves over time looks like x naught multiplied by a cosine expression. So the amplitude of this wave is kind of uninteresting. It just depends on how far we pulled things back originally. But the meat is this frequency term, square root of k divided by m. And if you think about it, this should hopefully be at least a little intuitive. For example, if you increase k, which is kind of like increasing the strength of that spring, then it results in a faster oscillation. Whereas if you increase m, the mass of the particle, there's a lot more inertia, and it results in a slower oscillation.
So this all relates completely to that simple harmonic motion section we did. We've looked at it, I should say.
This term, square root of k divided by m, has a special name. It's called the resonant frequency for our simple harmonic oscillator. And being a little more precise, I should call this the resonant angular frequency. This is always a little bit of an awkwardness with physics, where whenever you have some kind of cyclic process, when you give an intuitive description, it's natural to phrase things in terms of the frequency, the number of cycles that this process makes per unit time. But when doing math, it's often more natural to talk about the angular frequency, which you could think of as describing how much angle this process covers in radians per unit time. It's just the same as the frequency, but multiplied by 2 pi. So for example, if you have something like a cosine expression, which you might think of as describing the x component of a cycling vector like this, then the term sitting right in front of the t in that cosine is the angular frequency. This is why angular frequency makes the math a little cleaner. For example, in our simple harmonic motion, the term sitting in front of t looks like the square root of k divided by m, which I'm
don't worry about the details here, but just get the big overall picture, right? So this is a little bit too deep.
writing as omega sub r. Let's package all of that up and call that our solution in the simple case where there's no external force acting on our charged particle. But of course, what we're interested in is what happens when you shine a beam of light on this material, which intuitively causes this charge to jiggle, but the question is how much? In our equation, this looks like adding a new force term corresponding to the light wave. That force oscillates up and down, also according to some kind of cosine function, but this time with a distinct angular frequency that I'm going to call omega sub L. E naught here describes the strength of the wave, and then Q describes the charge of whatever particle we're modeling. As usual, it's a lot easier to think about when we only draw a subset of that light wave, and in this case, we're going to draw it on the plane of the layer of material that we care about. You might think of gusts of wind blowing our little ball on the spring up and down in a clean sinusoidal pattern. Or, as another analogy, it's similar to pushing a child on a swing. The swing would oscillate on its own due to the force of gravity, but you, as the pusher, are applying an external force, which itself is oscillating over time. Although a key difference here is that the frequency of that external force, in general, has nothing to do with the resonant frequency of that little oscillator. The better analogy would be if you're pushing the child on the swing with a cyclic force that has nothing to do with what the swing naturally wants to do. And my favorite part in literally trying to do this with my niece is that at some point she gently murmurs to herself, "This isn't how mom does it." Now, in trying to understand how much our charge is oscillating in response to the incoming light, let me start by just simulating it and plotting the result. You'll notice that there's a little startup period where it kind of has to get going, but then after that, mercifully, it looks nice and clean, just like another sine wave. Now you might be thinking, yeah, everything is sine waves, but it's important to understand that this one has a very different character from the sine wave we saw earlier. Earlier, without any external forces, the frequency of that wave came down to the spring constant and the mass, which is to say, it depends exclusively on material properties of the glass. By contrast, with this external cycling driving force, the frequency in that steady state is the same as the frequency of the light. And then in our first case, the amplitude of the wave was kind of uninteresting. It just depends on how far you pulled the spring out to begin with. But in the second case, the amplitude of this wave is actually where all the interesting stuff happens. Exactly how much will this charge be oscillating in response to the light wave? Again, I won't go over the full details of solving this, but any eager calculus students among you might enjoy going through the exercise where if you just guess that a solution looks like a cosine wave with the same frequency as the light, and you solve for the amplitude, you can get a concrete solution to this equation that looks like this. This is worth unpacking for a bit, and just to be clear, this is only describing things in the steady state, after things have kind of gotten up and going. A fully descriptive solution would be notably more complicated. As I said, everything interesting here comes down to the amplitude, which here looks like a large collection of constants, most of which should be pretty intuitive if you take a moment to think about it. For example, it is proportional to the strength of that incoming light wave, so the stronger the light, the more the oscillations. It's also proportional to the charge, which again makes sense. And the real heart of the matter comes down to what's sitting in the denominator here, the difference between the square of the resonant frequency and the square of the light frequency. And to build a little intuition, take a moment to think about what would happen if the frequency of the incoming light was something very close to the resonant frequency of this oscillator. This is analogous to the normal situation pushing a child on a swing, where the frequency of your force lined up quite closely with what the swing wants to do. In this case, running the simulation, notice how the oscillations of that particle will grow and grow and grow, becoming quite large over time. Some of you may know the famous example of the Millennium Bridge in London, where on its opening day, it started oscillating way more than the engineers expected it to. And what was going on is that the frequency of the steps of the crowd lined up very closely with a resonant frequency, causing this worryingly high amplitude. By contrast, notice what happens in the simulation if the frequency of the light, omega sub L, is something much smaller than the resonant frequency. For this particular simulation, it takes a little bit of a moment before things get into their full swing. Eventually, it finds a nice sinusoidal motion, but the amplitude of that motion is much more modest in comparison. So what our equation is telling us is that the larger the difference between those frequencies, then the bigger the denominator, so the smaller the overall wiggle to that charge. And again, this is something you can...
So that would be less of a phase shift, right? This is going to be the wave given off by the particle that's reacting to the light that's coming in. This is the wave that it gives off, and then that's the one we saw previously causes the phase kick, and therefore the wave to slow down.
See in the footage with my niece. As I'm applying a force with a frequency that's very different from what the swing wants to do, she ends up oscillating at the same frequency as my force, but she's going at a relatively low amplitude. Stepping back, what this means is that as you shine light into a material, like glass, it's not just that it induces wiggles in the charges of that material, but the specific size of those wiggles depends on the frequency of the light as a consequence of this denominator term. And the more those wiggle, the bigger the size of the second order wave caused by that layer, which in turn causes a bigger shift to the phase of the overall wave. Because a lot of different shifts to the phase are what causes this apparent slowdown to the light, it means that the amount that it will slow down ultimately depends on the frequency of the light. So that is the real reason why prisms work. You cannot truly explain the light separation until you get down to the driven harmonic oscillator.
Oof. So pretty heavy, but kind of neat, right? So there's a lot to it, like it says here in the textbook. A little bit complicated, and that textbook probably never actually covers it, to be honest. So dispersion, though, I think if you want to watch the rest there, he talks about the other examples. One of them was the mineral there, the calcite or lucite or whichever, gives the double refraction. So yeah, finish that video up if you like. But yeah, so I'm looking at this as dispersions, very, very, very heavily explained by wave property and not particles at all. One of my favorite quotes or stories to do with Newton, but partial reflection and partial transmission, which we know happens with light, right? So Newton couldn't deny that one. It's very obvious, right? So he proposed his so-called theory of fits. All right. So sometimes particles of light arrive at a transparent boundary in a fit of reflection, and other times they arrive in a fit of transmission, which is just bonkers that was ever said or written down. Obviously, along the lines of like a student, encouraging you to ask questions and not just accept things. I hope there were a lot of people around him that went, "You're not explaining anything, right?" Yeah. So waves are seen to do this, and of course so is light. And so obviously it's good evidence of wave property of light again. From grade 11, the if an object or a wave is going from slow to fast, you can see the wavelength got longer and so on, but the it comes back as an in phase reflection, so there's a partial reflection. So this is like a free end, and so it comes back in phase. And if we had the same thing, I was going to say if you had the other way around, but these are actual videos of it. Let me just pause quick and I'll find that one. All right, I've got my setup here. So you're going to see a pulse coming in from the right there. Oh, it's not going to allow me to, there we go. So a pulse coming in from the right, right? And then it goes into a slow material. So look at the length of that thing, right? It's like super long. It's like 1.5 meters long or so. It goes into the slow material. And the first thing I want to draw your attention to is, of course, it's a lot slower. You can see it, right? So this is just a light slinky and a heavy coiled spring, right? But what I also want you to notice is, this wave that's going in from the right. Watch what also happens. Now, right about here, I can sort of point it out. Watch this area here, and there's going to be a disturbance that's going to the right. And if I back up, you can see it going to the left, right? So if I back up, come on, wake up. Here we go. See that disturbance going to the left and back. So right now it's around here, then it goes to there. Okay, so that's the slow to fast. Let's go fast to slow. Actually, sorry, that was fast to slow. Slow to fast, I think, is actually more visible. Wait for it. Here we go. Yeah, way more visible. This is what I kind of meant to get first. I think I was saying it wrong because of that. But anyway, so we have a very obvious pulse coming in. It's going to go to a fast material. So let's pay attention to the transmitting through. So there's your partial transmission. Some of the energy went through, but a very obvious little pulse going going back, right? So see it wiggling back and forth in the middle there, right here, right? So you can tell that pulse travels off, and you can see that it's out of phase. Actually, no, that one's in phase, right? So the pulse was towards us, and it's still down in the screen. Okay. Anyway, so yeah, partial reflection, partial transmission, totally a wave thing, and you know, that's it for that part. I'll let you just watch those guys later if you're interested, but we're pretty much done here. So partial reflection, partial transmission, theory of fits that means nothing, or the fact that waves clearly do it, right? So lights seem to do it, waves do it, obviously good evidence of wave behavior of light. So some questions there to do with this stuff, and that is all for now. Thanks for watching.